There are multiple uncommon geologic hazards that, despite their rarity, can still potentially cause death and/or destruction. Starting off, lava tornadoes. While there has been a legitimate case of a volcanic eruption generating its own tornado, this is not what I am discussing here. Rather, what is being shown is a different type of a rapidly rotating air column that is actually a type of whirlwind, which can regardless still reach speeds of up to 50 miles per hour and similarly have a strong upward pull on any material it encounters. These are similar to fire whirls seen in some wildfires and form when hot air rises above the heat of a hot eruptive deposit, generally lava, combines with a minor local wind. This causes the current to begin rotating, which causes more air to rise that also begins rotating, creating a tornado-like phenomenon. And since these so-called lava tornadoes have a strong upward pull on anything they encounter, they can literally pick up boulder-sized fragments of still molten lava and then fling them potentially hundreds of feet away. These are quite difficult phenomena to predict, although they generally do not travel far beyond a lava flow edge before dissipating and are more likely to occur the greater the surface area of active molten lava there is in an area. Next, Tundra Explosions. These can potentially form giant craters more than 100 feet wide and deep and are a type of natural gas explosion primarily involving methane. This is why the more precise scientific term for these features are gas emission craters. Before I continue, I want to note that everything said at this point forward in this subsegment of my video on these craters is paraphrased from this linked scientific paper, which I recommend that you read for more information on this topic. Now, gas emission craters can technically form in any permafrost-rich area that has an underlying natural gas-bearing layer or series of layers. Due to rising world temperatures, what was once continuous permafrost coverage becomes more spotty, allowing lakes to form above non-permafrost patches of ground known as taliks. A section of talik then freezes, and natural gas, albeit primarily methane, accumulates there along with biogenic methane, with the former often migrating upwards through faults in the ground which act as natural weak points. Confined freezing then occurs, causing a buildup of pressure involving gas. Stratification of this material follows, with gas rising to the top, and this pushes overlying soil upwards without yet rupturing, although sometimes this uplift never happens, yet this process still continues. Eventually, if a large enough quantity of gas is present, the pressure becomes so great that an explosive pressure release occurs, ejecting gas, water, rock, and overlying soil, thus forming a crater. So far, this phenomenon has only been observed on the Yamal and Gaidan peninsulas of Russia, although they will likely become possible in other areas of the Arctic with abundant underlying natural gas reserves if world temperatures continue to increase. Blue lava. Technically speaking, lava is just molten rock erupted from a volcano, and it is almost always red to orange when it erupts. However, that is for lavas where silica is their main component. Sometimes volcanic areas can have unusually large concentrations of elemental sulfur deposited around them, especially around fumaroles. And I want to remind everyone that elemental sulfur has an unusually low melting point of 115 degrees Celsius and an auto-ignition temperature of 231 degrees Celsius. Certain fumaroles can easily produce temperatures that surpass both of these thresholds, causing any sulfur there to melt into a liquid and then ignite, where it burns with a blue flame that makes the ignited liquid sulfur also appear as blue. This phenomena is only visible at night at select volcanoes, most commonly occurring at Ijen in Indonesia and Dalol in Ethiopia. Burning of such produces large quantities of sulfur dioxide, with 100 parts per million or greater being immediately dangerous to life and human health and thus potentially fatal. Salt glaciers. Masses of thick ice are not the only material that can compose a glacier. In areas with large natural quantities of salt in rock units, salt glaciers can sometimes form. If rock units at some point become denser than underlying salt layer, it can cause the salt to act like a very viscous fluid and slowly begin rising. This salt can eventually break through the surface and advance downslope away from a vent, with such salt glaciers generally advancing at speeds of around a few centimeters a year. However, it is theoretically possible for segments of salt glaciers to advance by as much as 21 meters in a year, especially due to interactions within areas dry and wet seasons, and if any structures were to be close to such, they could eventually get bulldozed through. Salt glaciers are most commonly found in the Zagros Mountains of Iran. Hydrothermal explosions. While these most frequently occur in volcanic-related hot springs, they can also occur more rarely at hot springs that are purely tectonic in origin. Both of these generally occurs when a caprock of sorts, generally involving sinter, forms. Per a direct quote from the U.S. Geological Survey, hydrothermal explosions occur where shallow interconnected reservoirs of fluid with temperature at or near the boiling point underlie thermal fields. These fluids can rapidly transition to steam if their pressure suddenly drops. Since vapor molecules take up much more space than liquid molecules, the transition to steam results in significant expansion and blows apart surrounding rocks and ejects debris. Hydrothermal explosions can potentially form craters up to several hundred or even several thousand feet wide in rare circumstances, although they usually only form craters less than 100 feet wide. Hydrothermal explosions are seemingly impossible to predict, albeit rare, and most commonly occur in areas with hot springs where previous hydrothermal explosions had been observed. Limnic eruptions. Limnic eruptions can occur when large volumes of carbon dioxide are dissolved in a deep and stratified lake which overlies a source some depth below that is actively producing vast quantities of carbon dioxide gas, specifically a body of magma. This gas largely remains at depth in the lower section of a lake, not interacting with higher carbon dioxide pore layers. Eventually, if enough dissolved carbon dioxide is located in the lake, a limnic eruption might be triggered, whether it be through a volcanic eruption, an earthquake, or another possible reason such as a landslide. This causes the carbon dioxide dissolved in the bottom of the lake to rapidly rise to the surface, causing a runaway reaction where much of the carbon dioxide in the lake escapes in a short period of time. It thereafter advances downslope since carbon dioxide is denser than air, killing all animals and people the invisible cloud of gas encounters. Limnic eruptions, to the best of my knowledge, are only known to have occurred at these four bodies of water, all of which are close to the equator. Inland tsunamis. While tsunamis are best known as a hazard that can occur in the ocean, they can theoretically occur at any body of water, even hundreds of miles away from the near shoreline of an ocean. This is because all that is needed for a tsunami to be generated is for rapid displacement of a body of water to occur, either from a large landslide entering the water, or less commonly, a major earthquake rapidly moving a fault line beneath the body of water in a largely vertical manner. These inland tsunamis are most likely to occur in highly mountainous and rugged regions, most commonly areas with nearby glaciation or glacial deposits of some sort. Mud volcano explosions. While not true volcanoes, mud volcanoes can, on rare occasions, actually explode, producing a vast fireball that rises more than 1,000 feet into the sky, alongside ejecting large quantities of mud in a short period of time. This can occur at tectonic-related mud volcanoes which specifically exist due to the presence of underlying natural gas in one or more rock units. Groundwater captures some of this gas, and then as it rises, the groundwater would cause the gas to come out of solution, further propelling it upwards. Sometimes a very large batch of gas can rise all at once, sometimes due to fault movements or other reasons, resulting in large mud volcano eruptions on the surface. Since the main rising gas is methane, and methane is lighter than air, it quickly rises. All that is needed for the methane gas propelling the eruption to ignite, since it is highly flammable, is for an electric shock to be generated, equivalent or larger to one that would occur after rubbing your feet over a carpet and then touching a doorknob in winter. Generally, the static electricity that can ignite such is created by the motion of millions of tiny particles of mud banging against each other, or due to the larger rocks banging against each other in the upward mud plume that generates a spark. These explosive mud volcano eruptions have most commonly occurred in Azerbaijan and Colombia, occurring somewhere in the world an average of about twice a year. I hope that you found this video interesting. As a final note, I would like to thank this channel's patrons on Patreon and channel members on YouTube for supporting my work.